So, my dear student, you are welcome to another edition of our class today. So, we continue from where we stopped the other time. Don't forget, we are still treating our last time, the second time mock examination, past question. And if you can still recollect, our last class, I think I stopped on question 12. So, today, we are going to continue from question 13. So let's start from question 13A. Question 13A. Question 13A. So question 13A states that name the electric charge carriers for name the electric charge carriers. Electric charge carriers for name the electric charge carriers. Name the electric charge carriers for Roman figure 1. Gases, Roman figure 2. Electrolyte, Roman figure 3. Metallic conductor, Roman figure 4. Semiconductor. Now, for the first one, the electric charge carriers for gases are electrons and ions. Electrons and ions. Why for Roman figure 2 electrolytes? The electric charge carriers are only ions. Electric charge carriers for electrolytes are only ions. Don't forget, when electricity passes through an electrolyte, it's going to decompose into its constituent ions, and those ions will be either anions or cations. So for metallic conductors, the charge carriers are electrons. The charge carriers are electrons. While for semiconductor, the charge carriers are holes and electrons. Holes and electrons. Holes and electrons. Holes, don't forget, is a positive charged particle, while electrons is a negatively charged particle. So that is that for question 13A. 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 So let's go to 13B, Roman figure 1. 13B, Roman figure 1. B1. Explain how a gas. Explain how a gas can be made. Explain how a gas can be made to conduct electricity. Explain how a gas can be made to conduct electricity. So gas also conduct electricity, but for gas to conduct electricity, the pressure of that gas must be very, very low, and that same gas must be connected to a high potential difference. So the simple answer to that question is that when the pressure of the gas is low and high potential difference is connected to it, so that gas is going to conduct electricity. So that is the answer for question B1. Under. So answer now. Let me write it. Answer. The gas is going to conduct electricity under low pressure and high potential difference. As simple as that. Under low pressure and high potential difference. Now, Roman figure 2, B2. State three properties of cathode rays. B2. State three properties of cathode rays. Don't forget, cathode rays. What are cathode rays? They are fast-moving electrons. That are being ejected when in a discharge tube. So, because they are fast-moving electrons, their properties are the following. One, it is negatively charged. Because it's an electron, it is negatively charged. Two, it deflects towards the positive plate of electric field. It deflects towards the positive plate of electric field. Another property is that it can also deflect. It deflects towards the north pole of magnetic field. So you can see another one that it possesses momentum. It possesses momentum because it's a fast-moving electron, which means it has mass, and it's also moving with certain velocity. So definitely it must possess momentum. And five, it causes some materials. To flourish. It causes some materials to flourish. It causes some materials to flourish. It causes some materials to flourish. So if you check your note, you're going to see some other properties of cathode rays. So B3. B3 says that a coil, question B3, a coil of inductance is 0.008 Henry, that is L, 0.008 Henry. A resistor of resistance 9 ohms, R, is 9 ohms. And the capacitor of capacitor 0.002 farad. Capacitor 0.02 farad are connected in series to an AC source of frequency 600 over pi hertz. Frequency 600 over pi hertz. If the root mean square voltage of the source is 220 volts, that is V root mean square is 220 volts. Draw alpha. Draw the circuit diagram of the arrangement. Draw the circuit diagram of the arrangement. Draw the circuit diagram of the arrangement. So, in this case, because they are connected in series, my inductance or inductor is this. I will have my resistor is this. My capacitor is this. I can have my ammeter in this manner. Then, because it's an AC source, not direct current, it has a symbol of that. If it is direct current, we use this. Direct current, we use this. But for an AC source, you use this one. Then you close the circuit. In this case, I will have 0.008 Henry. L is 0.008 Henry. My R is 9 ohm. And this one is 0.002. The frequency is 600 over pi hertz, 220 volts. That's the diagram for the arrangement. Let's go to beta, the next question under that. The next question under that. So, the next question asks us to find the impedance, to calculate the impedance. We have to calculate the impedance. Then how do we calculate the impedance? That is beta. Find the impedance. My impedance Z equal square root of R squared plus XL minus XC, everything squared. Impedance Z equals square root of R squared plus XL, R squared plus into bracket XL minus XC, everything squared. So in this case, we need to calculate our XL, we calculate our XC, then we substitute it into that expression. Now, my XL equal omega L, that is 2 pi FL. So my XL will be 2 pi times F. What is my F? My F will be 600 over pi times, what is L? My L is 0.008. My L is 0.008. My L is 0.008. So XL will be 9.6 ohms. Then XC is 1 over omega L, that is 1 over 2 pi Fc. So in this case, if you substitute for that, we are going to have our x to be 0.42 ohms. Now, substituting all those in the expression, we have z equals square root of our r is 9 squared plus 9.6 minus 0.42 everything squared. Everything squared. 9.6 minus 0.42 everything squared. Use your calculator to find that. Our Z is going to be 12.86 ohms. 12.86 ohms. Don't forget the unit. Don't forget the unit. 12.86 ohms. Let's look at the next question here. Let's look at the next question here. The next question is gamma. Gamma. And you have to find the root mean square. Find the root mean square current. Find the root mean square current. Don't forget, Z equal V root mean square times I root mean square, or Z equal V naught times I naught from Ohm's law. Now in this case, using this, my I root mean square will be Z over V root mean square. So we have 12.86 over our V root mean square will give to be what? 220 volts. Therefore, I root mean square will be 12.86. 12. No, sorry, please. Sorry, please. From Ohm's law, V equal IR. Don't forget that V equal IR from Ohm's law. Therefore, V root mean square equal I root mean square times Z, and V naught, that is peak value of the voltage, equal I naught multiplied by Z. So because we are using this, then I will my R root mean square is a formula. That is V root mean square over Z. So my R root mean square will be 220 over 12.86. So our value for that will be, if we use our calculator, that is 17.11 ampere. 17.11 ampere. 17.11 ampere. 17.11 ampere. And the next question, that is theta. The next question, theta. Write down the sinusoidal equation for instantaneous voltage in terms of the time t. In terms of the time t. Write down the sinusoidal equation. Sinusoidal equation for the voltage. Don't forget, V instantaneous equal V naught sine omega t. So we need to calculate our V naught. So V naught equal V root mean square over V naught equal V root mean square multiplied by root 2. Multiplied by root 2, because V root mean square equal V naught over root 2. So if you substitute the value of V root mean square is 220. So 220 multiplied by root 2 will give us, then our V naught will be 311.13 volts. 311.13 volts. So that's our V naught. Then another thing we need in that expression is omega. Omega. So we calculate our omega before we can write that equation. So we calculate our omega. So our omega is 2 pi f. Our omega equal 2 pi f. So omega will now be 2 pi times 600 over pi. So I have 1200. So omega is 1200. Therefore, V instantaneous will be V naught 311.13 sine 1200t. 1200t. 311.13 sine 1200t times sine 1200t. That is V instantaneous. Our next question is C. Explain any two types of magnetic materials. 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 We have three types of magnetic materials. They are ferromagnetic, paramagnetic, and diamagnetic. C1. Two types. C1. Two types of magnetic materials. 1. Ferromagnetic materials, paramagnetic materials, and diamagnetic materials. So these are the three types of magnet. But the question says you should explain briefly. Now, what is ferromagnetic materials? The ferromagnetic materials are the materials that are strongly or easily attracted to a magnetic field. Ferromagnetic materials are the types of magnetic materials that are strongly or easily get attracted to the magnetic field. While paramagnetic material, they are magnetic materials that are weakly attracted to the magnetic field. But for diamagnetic, instead of them to be attracted to the magnetic field, so they repel towards the magnetic field. So these are the three types of magnetic material. So example of ferromagnetic materials, we have iron, we have steel. We have iron, we have steel, and then the rest. So we have C2. Question C2. State two postulates. State two postulates of Bohr's model. State two postulates of Bohr's model and its two limitations. State two postulates of Bohr's model and its two limitations. State two postulates of Bohr's model and its two limitations. Now, the postulate of Bohr is that a explained, or he postulated that electrons reforce. He postulated that electron reforce around the nucleus of an atom, and he called this orbit, he called it the energy level. The first postulate is that electron revolves around the nucleus of an atom in a circular orbit. He named this orbit energy level. The second postulate is that the angular momentum of an electron is quantized. The angular momentum of an electron is what? Is quantized. That is, they are the integral number. And also, the energy of electrons are also quantized. Energy of electrons are also quantized. So these are the three postulates of Bose. The first one, electron revolves around the nucleus of an atom in an orbit. This orbit, it named it energy level. The energy of an electron is quantized, and also the momentum of an electron is also quantized. Don't forget, we have, because the energy of an electron is quantized, they are in the integral multiples. We have different integral multiples of energy of electron. That's why we have En equal NHF. Where this N can be, we call it this N can be 1, can be 2, can be 3, can be 4, like that. It can be 4 like that. And this N is called quantum number. So that N stands for quantum number, and it takes value from 1, 2, 3, and then the rest. So two limitations of Bohr. The two limitations of Bohr are: it could not explain how fixed orbits for electrons are chosen at ground state. It could not explain how fixed orbits for electrons are chosen at ground state. And the second one is that it only accounted for hydrogen atoms or hydrogen-like atoms. That is, the Bohr only proposed the model for hydrogen atoms or hydrogen-like atoms. That is, the simplest atom, the non-simplest atom, which is the hydrogen, or some of the atoms that are very close or related to hydrogen. That's what the Bohr proposed for. So for any higher atomic element, so we cannot use Bohr model, except we use another or some other model that fits them. So this is where we are still going to stop for today's class. By next class, we continue from here. That is question 14.